In this video, we're going to take a look at an application of the derivative that's known as rectilinear motion, or simply linear motion, right? And when you think of the world that we live in, I don't think you can ever think of an object that is completely at rest, right? There's always something in motion. There's always something moving. There's always something changing. So the idea of studying motion is fundamental in understanding essentially our universe, and I'm not exaggerating by saying that, but here, as we get more comfortable with the concept of calculus and rates of change and so on, we start studying motion of the simplest type. So what do we mean by linear motion? Well, the word linear implies a line. So what kind of lines are we talking about? So basically, there are two possible axes. You have a horizontal axis or a vertical axis, right? So that's the linear part of it. And along this axis, you will have an object traveling either, if it's horizontal, either left or right, so you'll have an object somewhere there and either going this way or this way, left or right, and it might be changing direction at different times. And then if it's a vertical axis, then it's going up or down, right? So these are the types of lines that we're referring to. We're not even referring to like sloped lines, no, either vertical or horizontal. All right, and then we have a single object that's moving either left or right or up and down, right? Now in this sort of motion, then there are a few fundamental questions that we would like to be able to answer, right? So just here are some of those questions. At any given time, so at any given time, let's say t, where is the object on this horizontal axis? So where is the object? Where is it? Right? Now to answer the question about where, usually you would need some point of reference. And since we're talking about axes here, what we're going to do is assume that we have a point of reference, and we're just going to call it our origin like we normally do. So somewhere along this axis is a point that we're going to refer to as 0. And in order to answer this question, what we can do is, it would be nice if we could have a function where at any given time, if I plug in the value of time, it will give me a number that will give me the position relative to this origin. So for instance, the way we normally number a horizontal axis, you have the positive values to the right, and the further to the right you go, the bigger those values are. So we label it with values like this. And similarly, on a vertical axis, we label values like this, right? And then if we want to indicate maybe in the opposite direction, now we use negative numbers, right? So the negative there is really just saying that, relative to this reference point, this point of origin, this position is 1 unit away in the positive direction, whereas this position is 1 unit away in the negative direction, right? So we can think, when you think of a number line, we can actually think of it as indicating how far away are you from the origin and in what direction, right? Which then actually is consistent with our concept of negative infinity being down here and positive infinity being over here, right? So that's our first question. At any given time, where is the object? Next up, so if this object is moving either left or right, up or down, another fundamental question might be, how fast is it traveling? right? So how fast is the object traveling, and in what direction is it traveling, right? So how fast is the object traveling? So that sounds like a speed question. And in what direction? Is it going to the right? Is it going to the left? Is it going up? Is it going down? Right? So that's a direction question. You know, it almost sounds like we're in a physics class, doesn't it? That's exciting. We get to do a little bit of physics and math. Who would have thunk it? Right? So yeah, so this is an important question. How fast is the object traveling, and in what direction at any given time, right? Another important question might be, well, what if the object is not traveling? What if it's not going either to the right nor to the left? So is at what times, if any, right? So at what times is the object at rest? Does it ever stop moving, or is it in perpetual motion, right? So again, important question there. Another question would be, if it is in motion and let's say it is traveling towards the right, is it speeding up? So is it accelerating or is it decelerating, right? You know, so that's another important question. At a given time, is the object speeding up or slowing down? So speeding up or slowing down, right? So I think this is a good starting point as far as questions that we would like to be able to answer. I mean, there are other questions that are related to motion. In fact, some of those questions will be explored in greater detail in subsequent study of calculus and physics, right? And dynamics, you know, all those fun courses where everything just starts coming together. So, but I think these are good starting questions for us, right? So let's address the first one I mentioned about where is the object. Well, that one's going to be easy for us because we are going to be given what we're going to call a position function, right? So the position function, it will be a function of time, right? And it's typically denoted either s of t, right? Which seems a little strange to denote position with the letter s, but again, there are reasons for that. So it's either denoted s of t or x of t, right? And so this function gives the position at any given time. So I could if you say where is the object at 2 seconds from when motion started, then I could plug t equals 2 into this position function. I will get a number, and then that number would correspond to where the object is along my axis. It doesn't matter if it's horizontal or vertical. This function answers the question of where, right? So that's pretty straightforward. What about the how fast and in what direction, right? Well, let's define a quantity that is fundamental to the study of motion, and it's the concept of velocity. So the velocity is defined as the rate of change of position, right? So velocity is the rate of change of position. That's a definition, right? In other words, as this object is moving left or right, are the position values changing slowly like this, right? Or are they changing rapidly like this, where I'm getting dizzy, I can't even see my dot anymore? But yeah, so like, is the position changing quickly like this? I don't think my my thing can keep up with my movement. But anyway, there we go. So again, is the position changing quickly like this, or is it changing slowly like that? Right? Well, that rate at which the position is changing is defined as velocity. Now, this definition is something we can work with because we've dealt with rates of change before, right? So we've dealt with, for instance, the average rate of change. So, for instance, I could define the average velocity as the average rate of change of position, and I have a formula for average rate of change, right? But really, what we want is instantaneous. So we want to know at a specific time, not over an interval, right? It's not that the average rate is not an important rate, but that's algebra. We want to make use of what we know about calculus now. So if I want to find that at a particular instant, like how quickly this object is moving, then I would have to find the instantaneous velocity of the object. So this is our next definition, right? So the instantaneous velocity, so at an instant, so the instantaneous velocity of the, let's just say of the particle, so of the particle is the, again, and if for instance, if I just put the word instantaneous in front of velocity, then I'd have to put the word instantaneous in front of rate of change of position. So is the instantaneous rate of change of position. But we know how to find an instantaneous rate of change. So if I have a position function and I want to find the instantaneous rate of change of that position function, that's where the derivative comes in. So let's write that down. Now for the velocity function, we use the obvious symbol or letter, which is, in this case is the letter V. So we use V of t to represent our velocity function. And by definition, again, this is all it is, it's just a definition, assuming our function is differentiable. So if we have a nice smooth function, right, that gives us our position at any given time, if I differentiate that, then I will get the velocity of the object at any given time. So I'll use the S notation. So this would be S prime of t, or if you wanted to use the Leibniz notation, it would be ds dt, right? And that's the velocity, right? Now, because it's an instantaneous rate of change, you know, technically speaking, your velocity could either be positive or negative, or it could be zero, right? I mean, we've encountered that before, where at for different values of the independent variable, your derivative might be positive or negative or zero. So let's think about what that would mean, right? Now, the zero, if the v of t is zero, so that means the rate of change is zero, so there is no change in the position at that time. If the rate of change is zero, this answers the question about when is the object at rest, right? So if the rate of change of position is zero, then the object is at instantaneous rest, right? So the object or particle, I keep using them interchangeably. So if the velocity is equal to zero, the particle is at what we call instantaneous rest. So just at that moment, right? It's neither moving to the right nor to the left, or neither up nor down, right? So the particle is at rest. Well, that means In all other cases where the velocity is either positive or negative, then it must be either moving to the right or to the left. Now, or up or down. Now, if your velocity is greater than 0, then this means the rate of change is positive. So this means your position function would be increasing. So the position values would be getting bigger because your rate of change is positive, right? And what this means is the particle is moving in the positive direction, right? So if your velocity is positive, right, the particle is moving in the positive direction. So it means it's either traveling to the right if it's horizontal motion, or traveling upwards if it's vertical motion. So in the positive direction. Well, that means, so then there's only one possibility, right? So if a number is either 0, right, or I could say a function is either 0, positive, or negative. So if the velocity is negative, then what that means is the particle is moving in the negative direction. So it's either moving headed towards the left or headed downwards. So all of that just by looking at the derivative, right? And the thing I want to point out is that these concepts, the first derivative is not like new. I mean, we know how to differentiate it, and we know that it can be interpreted as an instantaneous rate of change. The only thing that's really different about this application is the fact that now the function represents something specific. It's not just any old function. It represents the position of an object along a linear axis, right? And then all these new terms, assuming these should not be new to you, right? But if they happen to be, then these are just definitions. We just define them in a particular way, and we're seeing how the definition relates to our understanding of the derivative, right? So that's how we can answer quite a few of those, right? Now, what about this question of whether the object is speeding up or slowing down? So here's the question: is the velocity constant, or is the velocity increasing or decreasing? So the analogy would be like if you're traveling in your vehicle and you put it on cruise control at, let's say, 65 miles per hour, then there is no change in your speed or your velocity, right? So is your velocity constant in that sense, or are you pressing down on the accelerator and pressing down harder, right? So are you accelerating, or are you decelerating? So you're not pressing down on the accelerator, but in fact you're applying the brakes. So is your velocity decreasing? So there is another rate of change that's important, and it is defined as the rate of change of velocity, and that's what we call acceleration. So acceleration, again, this is just the verbal definition. So acceleration is the rate of change, but now of velocity, right? So like how quickly, like when you look at your dashboard and you look at your needle that shows your speed, is it, are you going to 0 to 60 in 5.5 seconds, or are you slowly accelerating? That's what we're talking about here, and that's what we define as acceleration, right? But using the same logic as before, if I now want to find the instantaneous acceleration of the particle at a specific time, Well, that means I would have to find the instantaneous rate of change of velocity, right? So the instantaneous acceleration, right, as opposed to average, we're not going to compute those. We're interested in the instantaneous quantities. So the instantaneous acceleration of the particle is the instantaneous, let me get this off and let's scroll up a little more. So is the instantaneous rate of change of velocity, right? So then here's our third function that we're going to define, and it's acceleration. Again, these are all instantaneous. And for acceleration, we use a of t, little a of t. And that is, like we said, it's the instantaneous rate of change of velocity. So that means I have to find the derivative of velocity. So this would be v prime of t, or dv dt. But remember, velocity is already a rate of change. So like if I apply the Leibniz notation and write down what the definition of velocity is, so this is saying I would have to differentiate this derivative, right? Because remember, up here, this is another way that we could represent velocity. So if I'm going to differentiate this, then it actually means that acceleration is the second derivative. So this is our second derivative of the position function with respect to time. All right. So yeah, these two functions, velocity and acceleration, are vital in terms of analyzing motion, right? Now, as far as when an object is speeding up or slowing down, we have to consider two things. We have to consider its direction, because it could be speeding up going to the right or going upwards, or it could be speeding up going to the left or going downwards, right? Now, we have a way of determining the direction in which the object is traveling. That comes down to whether velocity is positive or negative, or in this case, zero, right? So for acceleration, if we want to answer the question about when an object is speeding up or slowing down, there are two things we have to consider. So if v of t is positive and a of t is positive, then what this means together is that this is when you're going fast, and again, you floor it. You know, you put the pedal to the metal. I think that's what you young people say, or maybe not anymore. But yeah, you floor it, and your velocity is increasing, and it's going in the positive direction. So when both of these functions are positive, the object is speeding up in the positive direction. So speeding up in the positive direction. All right, and that can happen. So now it could also speed up in the negative direction. That's when you throw your vehicle in reverse, and again, you floor it, right? So, and that will happen when your velocity is negative and your acceleration is negative, right? So if v of t is less than 0 and a of t is less than 0, then what that means is you're still speeding up, but in the opposite direction, in the negative direction, either to the left or downward. So you're speeding up in the negative direction. All right. So then it means if one way we can sort of describe this, an object is speeding up whenever velocity and acceleration have the same sign. So whether v and a are both positive, or v and a are both negative, right? So we can say that an object is speeding up when v and a have the same sign, meaning they're both positive or both negative. So v and a have the same sign, S-I-G-N. So that means if they have the opposite signs, then that's what would cause the object to slow down, right? So if velocity is positive but acceleration is negative, or velocity is negative and acceleration is positive, then the net result would be that the object would be slowing down, right? So let's write that down, right? So if v of t is positive and a of t is negative, then the object is still traveling in the positive direction, but velocity is now decreasing because your acceleration is negative. So that's when you're still going forward, but you're slowing down. So you're on the highway, you see the red lights ahead of you, you see that you have to slow down or maybe even eventually come to a stop, but you're still moving forward, but the rate at which you're moving forward is decreasing, right? So whenever your velocity is positive and your acceleration is negative, it means that you're slowing down but still going in the positive direction. So you're slowing down. So slowing down in the positive direction. Right, and then one other possibility. Now, so here I'm assuming that it's like the object isn't at rest, right? I'm assuming that there's movement in some direction. So if your velocity is negative and a of t is positive, this means you're still slowing down, but now in the negative direction. So the object would be slowing down in the negative direction. All right. So yeah, so basically what we can say, a nice little summary of this, is that when v and a have the opposite signs, when one's positive and the other one's negative, then the object will be slowing down. So this occurs when v and a, or velocity and acceleration, have opposite signs. Right? So it's not sufficient to just say that because acceleration is negative, then the object has to be slowing down. No, if acceleration is negative and the velocity is also negative, again, this is a situation where you're backing up, but you're speeding up as you're going in that negative direction, right? And similarly, it's possible where your velocity, your acceleration could be positive, but you could be slowing down, and that could happen in this situation, right? So keep in mind these important things. So I think what we should do is probably end with, it'd be nice to see an example of this, right? I think so. So let's look at an example. And what we'll do is we'll show you like what one of these functions look like. Well, it could be any of the functions that we know how to differentiate now. So let's say here is my position function, and it's 1/3 e to the negative 3t minus 1/2 t plus 2 and let's say, that looks more like a 7, but let's say plus 2, and let's say our position is measured in feet, right? And then t is measured in, so t is in, let's say, minutes. And for all, and in our models, we're not obviously gonna, if t represents time, then we are not going to consider negative time. I mean, negative time is a thing, but it's not going to be a thing for us in these models. So we're going to assume that our t in this case is greater than or equal to 0. All right, so that's the setup. Suppose we wanted to find the instantaneous velocity, right? Well, the velocity function would be the first derivative. So v of t. So let's apply our derivative rules now, and so our constant multiple rule, and then differentiate e to the negative 3t, we're going to have the e to the negative 3t, and then we're going to have to multiply by negative 3, and then minus 1/2, and then our constant goes away. So this now, and in fact, let's simplify this. So our instantaneous velocity function is, let's see, that's a positive 1 e to the negative 3t, so like that. So e to the negative 3t minus 1/2. The units for this, it is going to be feet per minute, right? Again, in terms of how you can figure out the units, just look at the units of your dependent variable here, which is your s, and then your independent variable here, which is your t. S is measured in feet, t is measured in minutes, so the rate of change of s with respect to t is feet per minute, right? So that's our velocity function. Let's go ahead and find the acceleration function. So a of t, which again, if we were to write it like this, would be the second derivative. Well, we can write it two ways. It is the first derivative of velocity, right? It's the instantaneous rate of change of velocity. Or we could say that it is the second derivative of the position function, because we've differentiated it twice, right? The first derivative has a specific name, the second derivative has a specific name, but as far as the process is concerned, this is our original function, right? Our position function, and after differentiating it twice, we'll get our acceleration function, instantaneous acceleration. So looking at this and differentiating it again, we got to use our chain rule. So e to the negative 3t times negative 3, and now the constant goes away. So here's our acceleration function. It's negative 3 e to the negative 3t. Now think about the units. Remember, we just said that the units for velocity are feet per minute, and of course the unit for time is minutes. So then the units for acceleration, if we use the same approach, it will be feet per minute, and it's often written as feet per minute squared. So this is feet per minute, or feet per minute squared, right? So these are our rates that we can use to answer lots of questions. Let's answer the question about when is it at rest, when is it traveling to the right. So let's assume that the motion is horizontal, right? So so for instantaneous rest, right? Let's figure out when the object is at rest. Well, the velocity would have to be equal to 0. So we would have to find the roots of our velocity function. And hopefully we get a solution, a value of t, where t is greater than or equal to 0. Well, let's see. So let's say e to the negative 3t minus 1/2, set that equal to 0. So add a half to both sides. Right, and we're not going to factor this because there's only one term on this side that has t. So we move the 1/2 over, then use the ln. So negative 3t is the ln of 1/2, and then t is, so then t is equal to negative 1/3 ln of 1/2. And whatever that decimal is, it's a positive number. You can verify. In fact, what I'm going to do is write the I'm going to rewrite this logarithm using some properties so that you see that it actually is a positive number. But if I take up the negative sign, right? So and I'll do this in stages. If I take up the negative sign, I'll have 1/3 ln of 1/2 to the negative 1 power. But 1/2 to the negative 1 power is 2. So this is 1/3 ln of 2. And then if I bring up the 1/3, I can make that a power 2. And I could have done it in one step, but I just wanted to do it in sequence. So we'll have t to the 2 to the 1/3. But we know the 1/3 power is equivalent to the cube root. So this is the ln of the cube root of 2, which is a positive number, right? So at this many minutes, the object is at rest. And there's only one value of time. So that means at all other values of t that are greater than or equal to 0, the object is either moving to the right or moving to the left. How do we figure out which is which? Well, we would have to, so moving to the right, well, we know that the velocity would have to be now greater than 0. So instead of having an equation, we now have an inequality. And what we can do, we end up solving this inequality in a similar manner because we don't have to factor anything. We don't have to factor, and this technically doesn't require the number line, right? But we do have to be careful because when if we add 1/2, so we add 1/2 like that. Take the ln, which again we can do that, so that gives us negative 3t is greater than the ln of 1/2. The inequality, when we divide by this negative 3, right, we have to change the direction of the inequality. So you have to be careful and have to apply those properties when solving inequalities. So your t is actually less than negative 1/3 ln of 1/2, which I will write in the simplified form that I have here. The ln of the cube root of 2, right? So whenever t is less than this quantity, then the object is moving to the right. Now, if we kind of put it and I'll draw the number line in a second, but if we then wanted to figure out when is the object moving to the left, so moving to the left, then your velocity would have to be negative. So it's pretty much the same setup, but then the inequality would again get flipped over, right? Because of this step, right? So it's the same exact steps here, but just we end up with a different direction. So this implies that t would have to be greater than the ln of the cube root of 2, right? So let's put this all together and actually show the number line for the velocity function, right? So for instance, here is our time axis. From 0, because it says t is greater than or equal to 0, and it goes to infinity. At t equals ln of the cube root of 2, right here, our velocity is equal to 0. So v of t is equal to 0 at that instant. For values of t that are less than the ln of the cube root of 3, our velocity is positive. That's what we solved right here, right? So velocity is positive whenever t is less than the ln of the cube root of 2. So in this interval here, v of t is positive, right? And then once you go past this value of t, for t greater than the ln of the cube root of 2, your velocity is negative. So maybe I'll put it down here. So your v of t is negative, right? So we can write a sentence kind of summarizing the motion just in terms of the direction and when it's at rest, right? So at t equals the ln of the cube root of 2, so the ln of the cube root of 2, the object is at rest. Right? And then over, or you could say during the interval, so over this interval, t greater than or equal to 0, but strictly less than the ln of the cube root of 2, the object is moving, so your velocity is positive there, so it's moving in the positive direction, so either to the right or upward. So the object is moving in the positive direction. All right, and then over this other interval, so once you go past this time, so over the interval t, so let's write it like this: ln of the cube root of 2 is less than t, which is then less than infinity. So I'm just using the inequality notation here. We can say that the object is moving in the negative direction. And it never stops after that, right? It continues. So it's always moving in the negative direction after t equals ln of the cube root of 2. All right. So that's our, so that uses the velocity just to analyze when is the object at rest, when is it moving in the positive or negative direction. Now, as far as speeding up, right? If we look at the acceleration, so remember a of t ended up being negative 3 e to the negative 3t feet per minute squared. Well, that means the exponential function itself is always positive, and then we're always multiplying by negative 3. So a of t is always a negative quantity, right? So a of t is always negative. So what does this mean? Well, what if we were to graph both like sign charts now, the one for the velocity and the one for a of t, right? So let's do them like this. So a of t is always negative. So a of t is always negative. But v of t does change sign, and we know when it changes sign at that ln of the cube root of 2. it is negative here, so v of t is negative in this interval, and then on this interval it's positive, so over here v of t is positive. So that means between 0, right, and the ln of the cube root of 2, the velocity and acceleration have the opposite signs, right? Different colors. That's why I'm using different colors. So whenever they're the different colors, it means the object is slowing down. Whenever they're the same color, it means the object is speeding up, right? So let's just write that. So we could say that the object is slowing down, and I'll just write the interval. It's slowing down between 0, remember this is 0, and our ln of the cube root of 2, so like this. And we wouldn't include this endpoint because we know at that instant it's at rest. So it's like this, our ln of the cube root. Oh, no, that's not the square root of 2, the cube root of. So the cube root of 2, right? And then when is it speeding up? Well, it's speeding up whenever they have the same color. So that occurs when t is greater than the ln of the cube root of 2. So just say t is greater than the ln of the cube root of 2. All right. So, with these two derivatives, right? The first derivative, which we call velocity, the second derivative, which we call acceleration, we can do a very detailed analysis of the motion of these objects, right? When the motion is linear. If the motion is not linear, then you need a little bit more advanced math, a little bit more advanced physics, and other areas. But the linear motion is always a good starting point, and it introduces these important concepts, these important rates of change, and how they affect how an object moves, right? So I hope you found that interesting, and I'll see you in the next video.